Now we move on to the next building block. We've gone through displacement, distance, we've gone through velocity, speed. Now we're going to look at acceleration. How do we build acceleration from what we've seen of the other building blocks? When the velocity of an object changes with time, the object is said to undergo an acceleration. Okay, so we're looking at here is something that is a rate, and the rate in this case is adding another unit of time into the denominator from velocity. So just like we started off defining the average velocity, let's take a look at defining the average acceleration. The average acceleration during a given time interval is defined as the change in velocity divided by the time interval during which that change occurred. So what we had previously was a delta x over delta t, which gave us an average velocity. Now we're going to take it the next step. And for those of you that have seen this before, this is actually the calculus. This is actually doing what's called a derivative in the calculus. So you're getting an introduction to calculus here as well. So the second derivative, or the second factor that occurs here, is now we're going to take the change in velocity over time. So we have the same type of representation and mathematical expression, but now it's velocity final minus velocity initial divided by the interval of time final minus time initial. So let's go back to an example here. Car example number 1. A car accelerates from its initial velocity of 10 meters per second to a final velocity of 30 meters per second in a time interval of 2 seconds. So now we take what we know here. We know we have an understood initial time interval of 0 and a final time interval of 2 seconds, and then our two factors of velocity, initial and final. And all we have to do again is put them into the expression that we've already developed. So now we have 30 meters per second minus 10 meters per second divided by the interval 2 seconds minus 0 seconds. So 2 seconds divided into 20 meters per second gives us an acceleration of 10 meters per second squared. Okay, I see a lot of problems in physics where students get the units of velocity and acceleration confused and you don't know what you're looking at. When you do this, if you're solving for acceleration, you better make sure that you have seconds squared in the denominator for the problem to be correct. Okay, so if we look at the relationship of the meters per second over second, you can see that we end up with meters per second squared in our answer. Acceleration then is a vector quantity having dimensions of length divided by time squared. Again, common units of acceleration, meters per second squared and feet per second squared. And again, you may have to get used to doing conversions between those two sets of units depending on what a problem asks you to solve. From the car example, on the average, the car accelerates in the positive x direction that its velocity increases at a rate of 10 meters per second. Okay, so it's an acceleration. It's a positive value. If it were a negative value, we would have deceleration, or the car slowing down. So graphically, let's take a look at how we look at graphical representations and are able to tell what we're looking at. Again, determining what we have set for the labels on our axis is going to tell us what our graphical plot is describing to us. So in A, where we have velocity on the vertical axis and time on the horizontal axis, and we have this constant acceleration or this constant growth in the numbers, you can see that we have a constant slope. Therefore, we have a constant acceleration. In the next one down, B, same graph, velocity versus time, constantly increasing speed, and we therefore have a constant acceleration then in its associated graph. Okay, so graph A, velocity, graph E, acceleration. Okay, graph B, velocity, graph D, acceleration. And then finally, C, here we've combined two graphs together. In this case, we've got a constant slope and then a slope of 0. So in this case, when we plot the acceleration based on that, you can see that we have constant acceleration for the first part, and then for the second part, we have 0 acceleration. So we're able to tell what's going on graphically by looking at one versus the other. Okay, if we have constant velocity, we have constant acceleration. If we have constant acceleration but it's not linear, we have increasing acceleration. And then finally, the two part, we have constant acceleration, constant velocity, no velocity, no acceleration, or constant velocity. And just a quick depiction, this just gives you an idea graphically or pictorially what's going on here. On the top line, we've got a race car. It's got the same length arrows over the top of it. So it's telling you that we have a constant acceleration. In the second line, you can see that we have an increasing acceleration. In the third line, you can see we have a decreasing acceleration with the graph. So it's just a pictorial to try to understand what goes on between acceleration and velocity. So, motion, equations of motion in a straight line under constant acceleration. You have to be very careful in problems. If the problem states that we have constant acceleration, that we include that in our representations and our relationships. This graph is probably a good thing for you to write down in your notebook. You should be keeping a notebook of all of the relationships that you come across that are going to be helpful in having you solve problems as you go throughout the course. So in this case, you can see we've got a definition for average acceleration. We've got a relationship then with a acceleration over an interval with time initial equal to 0. And then we have a relationship for solving for velocity when we have an initial velocity, which could be 0 and accelerating, and then a constant acceleration A. So our average acceleration. Over here we have the average velocity then in terms of velocity final, initial and final. And because it's an average, we divide it by 2, just like you would for any mean value. In this explanation, then we can solve for x, which is equal to the average velocity times time. Well, we define the average velocity in the previous step, multiply it times time, and we can then factor out the 1/2 here, and we end up with 1/2 of velocity plus velocity naught times time. Do some substituting for velocity equals velocity naught plus AT from the previous column over here. Do a substitution. Now we end up with an expression that says that the distance x is equal to 1/2 times twice the velocity plus the acceleration times time, all of that multiplied by time. And then combine our time factors into the expression and do some factoring. We end up with x is equal to v naught plus 1/2 the acceleration times time squared. Again, this is for a constant acceleration. So you need to understand how these each of these relationships are formed by doing substitution and from things that we've looked at earlier, but definitely keep these relationships handy as you are solving for different types of problems. Equations of motion in a straight line under constant acceleration. Again, we're just on the right-hand side here. We're going to start with the definition, which was really velocity is equal to x by t. We're going to move the terms around so that we have distance is equal to velocity times time. We're going to do a substitution here again for velocity. Velocity plus velocity naught times time. And then we are going to solve for velocity as a function of time, okay, which we were given, and we can then move the terms around so that we have time is equal to the difference in velocity minus velocity naught divided by acceleration. So again, it's just giving you ways to look at these relationships as we learn them and learn to manipulate them so that we can solve for the unknown, whether it's distance, whether it's velocity, whether it's time. If we continue on the left-hand column or the right-hand column, we end up with a relationship that says x is equal to 1/2 by velocity plus velocity naught times t. Okay, that's our relationship from the first column. Again, we start doing some substitutions for our values. We substitute velocity minus velocity naught divided by acceleration for time. Combine our terms, and then we end up with an expression then that we can solve for the velocity, or in this case, the velocity squared in a relationship. If we want the velocity, we take the square root of both sides and solve for just the final velocity. Although there isn't a subscript on there of little f, that's an understood final velocity, because you can see the other one has an initial velocity, or v naught. So in looking at your little cheat sheet table, if you're trying to answer questions of how far, how fast, how long, or at what angle, you can use any of these relationships then to help you solve for an unknown. Okay, and there are the examples that we've looked at. Again, keep this handy. Write this in your notebook and keep these relationships handy just the way that I've presented them here, and they will help you solve for specifics of a given problem. Equations of motion in a straight line under constant acceleration. Okay, velocity as a function of time. Average velocity as the mean value of initial and final values. Displacement as a function of velocity. Displacement as a function of time, and velocity as a function of displacement. Again, each of these will help you to solve for the types of problems that you're going to encounter in this chapter and throughout the next couple of chapters of this class. In the last section, we look at something called the free fall, where we've done everything on the horizontal or the x-axis. Now we're going to look at moving everything to the y-axis or the vertical axis. A free-falling object is an object moving under the influence of gravity only, regardless of its initial motion. So that should give you an immediate clue. When we're talking about only the influence of gravity, we've got a constant acceleration. That acceleration is 9.8 meters per second squared. Objects thrown upward or downward and those released from rest are free falling once they are released. Once they are in free fall, all objects do have an acceleration downward, which is the free fall acceleration, as I just stated, 9.8 meters per second squared. Even if you throw the ball up in the air, gravity is acting on it as a constant acceleration, trying to pull it back down. Once the ball reaches its apex, it's going to stop and gravity is going to take over. Assume the vector g is directed downward toward the center of the earth, and this will help you to solve your problems. A equals g. A is typically an acceleration upward or an acceleration above and beyond gravity. G is gravity itself. So in this chapter, we've developed and looked at relationships that help us define and solve for speed, acceleration, and distance, and we've looked at a little bit on introducing free fall. In the next chapter now, we combine everything together between x-axis, y-axis, vertical, and horizontal, and we come up with motion in 2 dimensions.